Another option we always have is t results, of course. So if we've got a trig integral that we want to use, we could always turn it into a polynomial by using t results. So where it's useful, if we're going to use the substitution t equals tan x on 2, and remember that means that sine x would be 2t on 1 plus t squared, cos x 1 minus t squared on 1 plus t squared. So it's useful for sine x and cos x when you see those in there. The t dx, because we've got to work out our substitution or our t result, if you like, for dx. So the t dx would be a half of sec squared x on 2, but sec squared is 1 plus tan squared, and remember t is tan. So we now have the t dx is 1 plus t squared on 2, so dx to t is 2 on 1 plus t squared, dx is 2 to t on 1 plus t squared. So that's our t result for dx. You don't have to derive it each time. Just like we quote the t result for sine x and cos x, we can quote the t result for dx as well. So why it's useful for sine x and cos x substitutions is you'll notice all three things have the same denominator. So it makes the cancelling and the fraction very easy. So let's do one. Dx on 7 plus 6 cos x. There's not a sine x on top, so I can't do a typical substitution. There's not a square there or anything like that. So I'll use the t results. So t tan x on 2, t result for dx 2 to t on 1 plus t squared. Subbing that in. Some people, when they sub in, they don't worry about the denominator because it's going to end up cancelling anyway. You just got to be careful. Remember that constant 7 needs to be multiplied by 1 plus t squared as well. So we get 2 to t on, and eventually when we tidy up the denominator, 13 plus t squared. That's our standard integral for inverse tan. A in this case will be the square root of 13. So I've got 1 over a, or 2 over a because of the 2 on top. So 2 on the square root of 13, inverse tan t on the square root of 13. Now we substitute back in for t, and t was tan x on 2. Be real careful on that, because remember x on 2 is the angle, so we don't put the 2 in the denominator of the root 13. It's tan of x on 2 on root 13, plus of course the constant. You don't have to do tan x on 2. I mean, if you want t to equal tan x, then what happens is the t dx, you end up getting the t on 1 plus t squared. What ends up happening, I don't know, I wouldn't derive it each time, because the pattern is simply, if you're going to use a substitution t equals tan x on a, normally that's going to be x on 2 for your standard one, then there's the derivation of it, but dx would just end up being a to t on 1 plus t squared. So if it's x over 2, it becomes 2 to t. Just x then, it became 1 to t on 1 plus t squared, and so on. So it's just always going to be a to t on 1 plus t squared. Notice, whatever's on the bottom, that's that to t. Okay, so that's just another technique when it comes to integration with trig.